Welcome everyone. Welcome to this day 3 of our 5-day data science workshop on credit risk scorecard. Let's just quickly recap what we did so far. So far what we have done is logistic regression concept we understood, and we imported data in Python, and we did a train test split. We have understood the concept of training and testing. And as part of training testing, we are using a validation approach. As such, we splitted our data into three: development sample, validation sample, and a holdout sample. This is the broad framework which I explained yesterday in our day 2 session, where we get loan applications, and the loan applications are either approved or rejected. The approved cases which are actually disbursed. Once the loan is disbursed, customer pays the money, or maybe customer may default. Depending upon that, customer is classified as yes or no. This historical data is actually what we use while building a credit scorecard. So probably as a bank, I would have given loan to many customers. Say I've got historical 100,000, 1 lakh data points available. All of those loans, I will have tagged them as default, no default, and that entire data set in form of a table, which I've shown here in a representative format, is available. Now, when we build the model, we are not going to exactly say this customer is going to be a defaulter. This customer is not going to be defaulter. What a model is going to give is what is the probability that this customer is likely to be defaulter. If we know probability of default, 1 minus probability of default is the probability of not defaulting. So we will always speak in the terms of event of our interest, and the event of interest in our scenario is default. What is the probability that this customer, if I give a loan, is likely to default? So whenever I use the term probability in credit risk scorecard, it means default probability. Then we went ahead and understood this logistic regression sigmoid function, how the linear regression is transformed, and the transformed format of linear regression is actually logistic, where we take the target in the target variable. This is the column target. In target variable, we have values 1 and 0. But when we summarize it or roll up at a variable level, yesterday we saw that when we aggregate data at gender, the summarization gives you probability. So we, rather than modeling probability as a function of the independent variable, we model the odds, log of odds, as a linear equation of the variables. So what we'll do is, we will today first build a simple logistic regression model using one variable, and then using the equation we will derive the probability, and then we will get into outlier treatment, missing value imputation. Total number of observations which are given in the file is 20,000 records. Of the 20,000 records, there are 1,399 records which are defaulters and 18,601 which are non-defaulters. Here I would like to inform you, in a home loan kind of a product, you do not have such a high default rate. 7% is what I'm showing in the data is the default rate. In home loan kind of a product, you will expect 0.25, 0.3, 1%, max to max 1% default. However, the default are low, so in order to build the models, we typically tweak the default definition Like anyone who has missed two EMIs, we will say has defaulted. Probably that customer later on might have paid the money. So one, we tweak the definition. Second is when we take historical data, we take all the defaulters data point and we take a partial non-defaulter data. For example, if I have got overall 1 lakh observations, say assume I've got 100,000 observations historical data available with me. In that historical data of 100,000, there are overall 1,399 defaulters. If this is the scenario, my default rate would be just 1.4 percentage. However, what I do, I take all the defaulters and I take only a partial set of non-defaulters. The moment I take a partial set of non-defaulters, my default rate has increased. So these are certain concepts called oversampling, undersampling. Those are certain concepts. The entire reason of doing this is so that we have sufficient amount of defaulters in our data in comparison with the non-defaulters, so that we can build a good model. So this is what the data set which has been made available to you. Now we have to build a model. So as I mentioned, we will build single variable logistic regression first, and from that logistic regression we will try to get the probability. Yes, this is imbalanced data set. So Vatsalya is saying that, is this an imbalanced data set? Yes, there are concepts called balanced data set, imbalanced data set, and here it is a imbalanced data set. Logistic regression can handle imbalanced data set, and we can build a good model using logistic regression on imbalanced data set. Okay. Let me go to Excel. Now here, this is the entire data, and on this entire data, I have done insert and then pivot table, and after having done pivot table, I have got this kind of a summary. This summary is where I have taken gender variable. And in gender variable, when I do the summary, you can see that 6.87 percentage default rate is what we observe in female, and 7.01 is the default rate in the male category. Overall average is 7 percentage. The intention of showing this number is we are going to take one variable gender and build the model. I now am going into my Jupyter notebook, and the syntaxes that are very essential to be executed is import pandas as PD. I load the file. I would like all of you to do these steps parallelly. This is a shape command. The shape command, when you see this 20,000, it's saying these many rows are there, and 27, it says these many columns are there. Head is just to display data, need not run. And for now, I'm skipping train test. I'm directly jumping to a single variable model. We have already seen train test. I am building the model on the entire data set. The reason is I want to explain the calculation of probability. So I'm taking this entire data set, target as a single variable logistic regression, target as a function of gender. What I will do is I'll put this message, this code on the chat box. And I'll give you time to launch your Jupyter notebook, execute the code. So I execute this function, control enter, and here I get my coefficients. This is my coefficients table. If you would note that this coefficient table I have copy pasted in the PowerPoint presentation here. So this is the Excel summary which I have shown. This is the single variable logistic regression code. This is the summary. I would request all of you to reach till this point, and then I'll explain the interpretation of this coefficient table. Let us now understand the interpretation. In this, for now, I'm going to focus on the coefficients. This is the intercept. This is my beta. Now in gender, we have got two categories, female and male. The beta for male category has been given to us, but the beta of the female category is not there. When a categorical variable is used, one of the category becomes your baseline. And the category which is baseline, the beta coefficient of that category is assumed to be 0. So the beta of female is 0. So here I have put down those two separately, intercept and beta of male. We know probability equation is 1 upon 1 plus exponential of minus z, where z is, from the above equation, z is minus 2.6071 plus 0.0219 into male plus 0 into female. Beta coefficient of female is 0. So even if I do not write this part, it's okay. But anyways, for clarity purpose, I have written this on the screen. Now assume there is a customer who is male. If I compute the Z part of it, in that case it will be minus 2.6071 plus 0.0219 into male, and because it is male we will assume it is male, so it is 1. So the Z will become minus 2.5852. And if I replace this Z in this equation P, I get the probability of male is equal to 0.0701, and this 0.0701 in percentage terms is 7.01. Likewise, if I compute Z for female, in case of female, the male component 0.0219 into male will not come, and the beta of female is 0. So Z will remain minus 2.6071. And if I take this Z value in the P value equation, probability equation, 1 upon 1 plus exponential of minus Z, I get the probability of female as 0.0687, which is anyways at the summary level, it was 6.87. So the point is, at one variable I have explained how the regression equation has captured the probability into a model, into an equation, and when I solve that equation, I can get the default rate. I hope this simple application, simple calculation helps you understand how logistic regression has captured the probability, the default in the model. Any questions? Okay, we have now understood the concept and the calculation part of logistic regression. So what we'll do is we now move on to the next topic, which is basically outlier treatment and missing value imputation. So before that, I'll split the data into dev, val, holdout. Here we are making use of a function which is split. numpy.split. This split function is already available in numpy, and to that we have to say that okay, we want three fractions, and one fraction is up to 0.5, another is up to 0.8, and the remaining fraction becomes the third. So these are the three sequential fractions in which I want to put my data. When I see length, it shows me 10,000, 6,000, 4,000. And yesterday I explained that whenever you run this code, you have to cross check the default rate with the population and the samples. So I'm just executing those commands. Now, one of the important step before we actually get into modeling, so is to understand the metadata and do a profiling of each and every variable. There is a function called describe. For now, I'm using a describe. There are many more functions in Python which gives you more detailed profiling. For now, I'm not going into those functions. I'm using the simplest one, which quickly gives me output in the Jupyter notebook only. So when I see that prospect number, it says there are 10,000 observation. 10,000 why? Because I am doing profiling on the dev sample. Loan dispersal, there are 10,000. Asset cost, there are 10,000. So if I just quickly scroll, it shows 10,000, 10,000, 10,000. But somewhere here, it shows me 9914. This 9914 observations indicates that probably this variable has got certain missing values. So one of the important thing when we do profiling is to see whether there are missing values or not. Second important thing when we do profiling is to check summary statistics of important variables. For example, loan to value. I'll just go at the last column, loan to value. So this was the code, Rajshri. This is the code I executed. Okay. So I'm just quickly jumping to the last column. Please understand, when you do this profiling descriptive statistics, domain knowledge is essential. Okay. If you have domain knowledge, you will be able to say whether that variable is correct or not. For example, in a home loan, if you are buying a property which is 1 crore value, bank is not going to give you 1 crore 10 lakh rupees. Bank will give you any amount which is less than or equal to 1 crore. Okay. So here when I see LTV, the entire statistics, the first one is mean, standard deviation, minimum, maximum. And then first quartile, second quartile, third quartile. So mean and standard deviation. So if I see that, it shows me mean is 66, minimum, standard deviation is 14, minimum is 40, and maximum is 95. So what it is showing is all the loans has been disbursed with a loan to value between 40 to 95. If I see such a summary statistics for a loan to value variable, it will give me the confidence that all data point, at least for the variable, is correct. Tenure. Let's take another variable, tenure. Home loans, you know, can be taken for 3 years, 5 years, 10 years, maximum. Some companies gives 20 and some companies give 30 also. But that's what the maximum range is. So if I see here, tenure is given in months, 240. 240 means 20 years. So Maximum loan in the book is of 20-year tenure. Minimum is around 57, 60. 60 is what minimum is, 5 years. So this is where the profiling comes into play. Any questions at this point? There are many things to be seen in profiling. I'm just covering at a very high level the sequence in which you do the model development. Okay. So one of the important element is metadata understanding, understanding each and every column. Then second is understanding the statistics, descriptive statistics of each and every column. That is also essential. If there are any questions, let me know at this point of time, else we move forward. After profiling, we have outlier treatment. What is outlier treatment? Extreme values in data are called outliers. Any variable having an extreme value is considered outlier. Now, how do you detect outlier? The first question is, if any column has got an outlier, how do I find whether there is an outlier or not? In descriptive statistics, we use something called as graphical methods. Okay. And the plot which we use in graphical methods for outlier detection is called box plot. Utility of a box plot is it quickly helps you find outliers in data. So if I run this piece of code where I am making use of matplotlib and cbon. Just for your knowledge, if you don't know much of Python, matplotlib is a package in Python which is used for plots. Cbon is another package which is actually built on top of matplotlib. Cbon helps you get better visualizations. Okay, so these are the two important packages. Now, if you do not run this line of code, Control Z, if I run the code without this line, what will happen? The plot is not going to come. In Jupyter Notebook, when you make a plot, to ensure the plot is visible, we have to add this simple one line statement, matplotlib inline, which says that kindly show the visual, the chart in line in the Jupyter Notebook itself. So this line is to say that the graph should be shown here itself. Plot.figure, this part of the command is just to say that I want a plot which is 9 by 5 in size. Here I'm making use of cbon. If you see, import cbon as SNS. So I make use of cbon.boxplotlib. In X, I'm passing one of the variable vintage in business. How will it come to know this variable is to be taken from which data set? I have to specify the data has to be dev. I can put another data also. Then it will take this column from LRDF. Show means. If I say show mean on the box plot, it will also show me where is the mean. Width equal to 0.5 and palette. There are certain palettes, predefined palettes to give the look and feel. That's what is available in Seaborn. So I chose color blind and I just label the title and X label, control enter. I get the box plot. So this kind of output. I'll explain the box plot so that you understand in more detail. How a box plot is made. In the box plot, the box which is at the center, this is your Q1. What it means is 25% of the observations are to the left of Q1. So wherever is this Q1 value touching, so it is somewhere around say 20. So 25% of the people, customers in the data have vintage in business less than 20 months. Is the meaning of that. This one is Q2. Q2 is also called median. If I take data to the left, it means 50% of the data is to the left of it. This is Q3. By now you would have understood, if I take all observations to the left of it, it will mean 75% of the observation, or the other way of saying is 25% of observation is above it. So that's what Q1, Q2, Q3 meaning is. Between Q1 to Q3, you have 50% of the data point. So this is what the meaning of. These are called as lower control limits and upper control limit. Lower control limit, upper control limit. How are lower control and upper control limits determined? By the way, this middle 50 has got a term which is called as interquartile range. IQR. Now, how are these upper control limits and lower control limits determined? There is a mathematical formula. The mathematical formula are upper control limit is equal to Q3 plus 1.5 times the interquartile range, Q3 minus Q1. That is the formula. And the lower control limit formula is Q1 minus 1.5 times interquartile range, that is Q3 minus Q1. If there is any value in the data which is above the upper control limit, or if there is any value which is below the lower control limit, assume if there is any dots on this side of the data, just like we have got these dots. In that case, we say there is an outlier in the data. Outliers in a simple term is extreme values. If you have not understood the outlier so far, I'll give a very simple example so that you can understand the definition of outlier. I want to calculate average wealth ownership of people living in the city of Mumbai. So assume I have the entire database of all people who are in Mumbai and their wealth ownership. So I do summation of wealth of all the individuals divided by number of individuals. That is the average wealth ownership of people living in city of Mumbai. However, this calculation would be impacted because I am counting Mukesh Ambani also in this. And Mukesh Ambani's wealth will increase the overall average for everyone. So Mukesh Ambani's wealth, which is an extreme value, those extreme values, when we do analysis, has to be treated. I'm not saying those extreme values has to be dropped. I'm saying for model development, we have to treat them. And the method of treatment is these extreme values, whichever value is above the upper control limit, we replace them by the upper control limit value. So in this case, I see upper control limit is around 116, and this 116 is in months. So I'm rounding it off to somewhere around 120, and I'm saying that if any value is greater than 120, make that 120. This is the concept of outlier treatment. In case there would have been any outlier on the lower side, assume here if there would have been any value here, we would have brought that value to the lower control limit side. So any value outside of upper control or lower control, they are replaced by either the lower control or the upper control, depending upon which side the outlier is present. So quickly execute the code. I'll wait for a while. Okay, and one thing what you have to remember, whenever you do outlier treatment, you should always create a new column. So here on the left hand side, if you see, I'm making use of the column vintage in business, which is an existing column, and any treatment which I have done, after that treatment, I've stored all the values in a new column. The reason why we should always create a new column is, for example, all of a sudden you think, okay, I don't want to cap it at 120, but I want to do it at 132. In case you have overwritten the existing column, now you will not be able to change it unless you run the code right from the beginning. Whenever you do any variable transformation in machine learning, the concept is create a new column. Do not replace existing column. All existing columns should be kept as they are. Okay, let's move on to the next important topic, which is missing value imputation. Now the question is, why should we do imputation? The reason is statistical packages discard the records or the cases having missing data in any column. If you have not understood this, I'll try to explain this with a practical example. But before that, let us find out all variables which have got missing. One approach of getting missing is I keep observing this data by scrolling for each and every column and then say where are missing values. The other approach is we run two lines of some Python code where I'm saying that check is there any null values. Null means missing. And here when I am saying check it, I'm saying across axis equal to 0. When you say axis equal to 0, it means apply this function column by column. Okay, so in Python, when you have a data frame, axis equal to 0 is columns, axis equal to 1 means rows, and here we want to find columns which have got missing values. So that's why I have written x is equal to 0, and then I am dropping all the records where there is no missing. So in case I do not write this line of statement, what will happen is you will get an output something like this. It says prospect number does not have any missing. There are zero missing. There are zero missing. But I don't want this output like this. I just want to focus only on those observations where there is a missing. So I write this line. Now it is very clear. This has got missing and marital status has got missing. So these are the two columns which has got missing. So here is the code to find columns having missing values. Quickly execute the code. So let's understand why imputation. I have upfront mentioned that statistical packages discard the records having any missing data. What I am trying to explain with this statement is, let's say I'm taking this distance from office variable and building a model, and this time around I am using dev data. So before I use dev data, let me add one more syntax here, dev dot shape. What dev dot shape is showing me? There are 10,000 observations. So the number of rows are 10,000. I am building a logistic regression model using 10,000 observations. And I am doing a summary. When I run this line of code, here when I observe the summary result, it is saying that it has considered only 9,914 observations. Where are 86 observations gone? The 86 observations have not been used because the variable distance from office has 86 rows where it is missing. This is what I was trying to explain by this statement, why we need imputation. Imputation is required because if there is any missing, those rows will not be considered in model development if you do not impute. Impute means you have to give some appropriate value to those missing. Okay. Now, how do we impute missing is the question. There are various approaches of imputing. One approach is do nothing. In this approach of do nothing, you will actually lose information. This approach can be taken only when you are confident that those are wrong records. Only when you are confident that those records where there is a information missing is a wrong record, you should take the approach of do nothing. Otherwise, there are various methods of imputation: mean, median, mode value imputation. You can use a non-parametric machine learning technique called k-nearest neighbor technique. You can use a linear regression technique for imputation. However, we cannot use linear regression for imputation in logistic regression technique because there is something called as multicollinearity, and because of multicollinearity we have to avoid linear regression approach. You can use some surrogates or logical imputation approaches, or there is a package mice. We can use a mice package for imputation. All of these are very detailed topics. For now, I have explained why imputation is required. I am taking the simplest of the approach where I am going to replace the missing values with mean. So let me quickly see what is mean. The mean of distance from office. How far is my office, the customer's office, from the existing residence? It's saying average is 23 kilometers. Now here what we are going to do is we are using a fill NA function. What we are saying is if there is any value which is missing, not available, replace it by the mean statistics. So this line of syntax is going to replace all missing with the mean, and once again, because I'm doing some variable transformation, some variable changes, I am going to create a new column. Having created a new column, if I now build the model with this new model, this new variable where missing has been taken care, this time around I'm going to run regression with this variable. Control enter. You see all observations have been taken into consideration. This is the reason why missing value imputation is to be done. The second important reason why missing value imputation has to be done is once you have built the model, you will have to deploy and implement it for future purpose. In future, when you get a record which has got missing information, in case you have not done the imputation, the model will not be able to give you the probability for that record, because at the time of model development you ignored records with missing. So that is another reason why missing has to be treated. What I'm trying to say is if your business is such that there will be certain records for certain columns, they will have missing value, and at the time of building the model you ignored those records. So model has not learned how to treat records with missing information. As such, you cannot apply the model to make a prediction. In that case, your model will be useful only for those observations where complete information is there. Those records where information is not complete, you will not be able to use the model. To overcome this challenge, we have imputation techniques. And the imputation techniques, as I highlighted here, there are various imputation techniques which we can use. One of the basic one is mean value imputation, which I have showcased how to go about using. So that's what we have done. Quickly try out the missing value imputation at your end and confirm back. Okay, so what we have learned in today's session is we have learned how to do the calculation of probability. We have learned outlier treatment. As part of outlier treatment, we used a box plot to visually see if there are outliers in data. Then we have learned the importance of missing value imputation, why we need to impute the missing values in data. If there are missings, those observations which have got missing will not be considered as part of the model. That's the reason we have to impute. And secondly, if we do not impute, we cannot use that model in future for observations having missing value. As a small practice exercise, what I would suggest is you build a model using two variables. Say one is gender and second is LTV. To build a model using two variables, what you will have to do is a small change in syntax. For here, example, if I have to pass two variables, I have to put a plus symbol. Try building a model using two variables, and when you get this, you will get a beta coefficients. Now from the beta coefficient, you assume the person is say male, and the distance of that person from office is say 10 kilometer, 15 kilometer. Using the equation which I have explained here, compute the probability. This will help you gain confidence on how probability is estimated in logistic regression. Okay, so that's a small practice exercise which I leave for you for our session which will happen on Friday. We have covered these concepts, so we are almost close to end of today's session. In the upcoming session, we have to learn visualizations, pattern detection, and how to find important variables in the model. Any questions? I would wait for those people who have any queries. Those who do not have queries can feel free to drop. Thank you. Bye bye. Okay. Thank you. Bye bye. See you on Friday.